So welcome to the Women in Science Day. Thank you guys so much for showing up. Today we're celebrating the UN's International Day for Women and Girls in Science. But this is really a platform. This is a platform to show you what Aarhus University's women are doing in their research. And we try each year to get a diversity in our types of sciences presented. And I hope that this year you'll see that we've got a few more from last year. And we really are excited to show you this. And this is a proactive platform. So you guys are aware of gender equality issues, you're aware of this, and this is how we have chosen to approach it. Just to give a platform that shows what women are doing and how amazing it is. So thank you very much. And without further ado, I will hand it over to Marianne.
So I'm here today to talk to you about air pollution and how we trace the sources and the processes going on in the atmosphere. And first I give you a little bit introduction to who I am and what I do in my research. So I use tools from analytical chemistry to investigate the sources to air pollution, specifically particles in the atmosphere. So I have been looking at particles from wood stoves and in different types of environments, in forest and marine environments, also in the Arctic. And what we do, I will explain a little bit more at a later point. But you see this first picture, I'm very happy. That's when I acquired funding for my HPLC QTOF-MS system. And we were very happy to get that installed. So during recent years, you know, when you work with pollution, then sometimes it's a little bit, people give you money and you will tell them all about all the problems that are in the world. So to do something a little bit more solution-oriented, we have also been doing some research on developing of new bio-oils, biofuels, where we convert biomass into a fuel, and then we investigate the chemical processes going on. So a couple of years ago, I was fortunate to go on a sabbatical, a research stay in California, at University of California in Berkeley. And luckily enough, my family was able to come along too. My husband got a position there while we were there, and our two kids went to school and learned a lot of English and how it is to live in a different country. Traveling, it's nice. You go to different places and you can go and explore, and on some days the view could look like this, but then on other days it could look like this. So this is a view, you see it's the same picture, but just on 2 different days. So over here on this side we have 8 micrograms of fine particles per cubic meter of air. And then on this other day, it's about 147 micrograms per cubic meter of air. So this could be today in northern India, it could be in China, large parts of Asia. In the 50s, it could have been Los Angeles or London. The air could look like this on some day. And it's not just what it looks like, but it's also when you're out there, you can taste the smog. So this is not haze. These are particles that you can see in the air, particles from different sources. And then what we are investigating is what are those sources. So what can we do to reduce the pollution levels? To explain a little bit more what a particle is, I have a picture here. So this huge thing is a hair. And then you take your hair, and then imagine you have this little bracelet around it of the small pearls here, and they would be the size of the particles in the air. So we have particles that we call coarse particles, these blue ones here. They're from 10 micrometers and smaller. And then we also have the red ones here. They are what we call fine particles. So you see they are little string of pearls around the blue ones. So they're really, really small. And still we can see them when there are enough of them in the air, because they interact with the visible light and disturbs our vision. So if we have a really strong microscope, we can also see what they look like. So some of them, you can see, they look like an alien or something like that, but this is just a pollen. Then we have a soot particle here, so from a combustion process. What you see here in the background is just the filter where the particles were collected on for this microscope analysis. And then we have other types of particles. This is from a metal smelter and mineral particles. So they can look like very different things, and these are the particles that are emitted directly. So air pollution with aerosol particles is really one of the grand challenges we have today. The WHO estimates that 3.7 million people die prematurely, so before we expect them to die every year due to ambient air pollution. On top of that, you can add the indoor air pollution, especially in developing countries. But if that wasn't enough, the particles also affect climate. So they scatter directly the incoming sunlight and reflects part of it. And then they also affect the cloud formation, cloud lifetime and properties. And it's really one of the largest uncertainties we have today in our understanding of climate and climate change. So, before I talked about the particles that we emit directly from different combustion processes or biomass burning processes, so this chart focuses on the organic part of the particles. So we have both the direct emissions forming organic aerosols in the atmosphere, but then over here we have a different type of formation. So when you're in a spruce forest, you have this nice smell of the spruce. Well, this is just organic gases coming out in the atmosphere. Later, Bodil will explain why plants emit all these gases. Because it's actually about 140 teragrams per year of organic gases emitted from spruce and those type of trees. So they emit some compounds called monoterpenes. So this is really what gives you this nice Christmas smell of trees. And they have a very short lifetime in the atmosphere. Within an hour or so, they're oxidized from being a volatile organic compound until something which is semi-volatile. And this semi-volatile compound, it has different possibilities. It can be oxidized completely to CO2. It can also deposit back to the surface. Or some of them would have a vapor pressure that's so low, so they go from being a gas and then to condensing on the particles already in the atmosphere, or contributing to formation of new particles. You can compare it to when you're boiling water, and then you put a cold lid on top of the boiling water. Then you can see the water vapor will condense on the lid. It's more or less the same process you can have here. So the forests here also contribute to the particles in the atmosphere. And of course, we can also have organic gases from man-made combustion processes. But we can trace these molecules, so we can go out and collect the particles we have over here, and then we will know what the sources were and which processes formed these particles. So how do we do that? Well, it's just the same techniques that they use in the crime scene investigation. It is really the same techniques, except that we go out and collect the particles in different places, go to forest areas or marine areas in different places, and collect the particles. Then we have the particles on a filter. Back in the lab, we extract the particles. So we have a little sample here. And then we analyze by the HPLC QTFMS that I showed you in the beginning. So this method enables us to separate each molecule we're interested in. So each peak you see here belongs to one specific type of molecule, and then the size of this peak can tell me how much is there of this molecule. So I can use this, for example, to trace biomass burning, because I know there are some specific molecules that come from the biomass burning, and if they're in my particles, biomass burning contributed to my particle sample. So in my research group, we have been doing investigations in many different places. The places in Europe, we have typically been traveling there ourselves to collect the particles. Also have students who went to Station Nord in North Greenland to collect particles. But then also the advantage of collecting particles on a filter is that you can put that filter in the mail and ship it to other places. So through collaborations, we have been analyzing filters from China, from the Amazon, and also from different places in the United States. So this is from a study we did in Northern Europe during winter a couple of years ago. So the idea was that we collected particles at the same time at different places in Northern Europe. And then we could compare the sources to these particles that we collected. So the samples were collected for 1 week each. So each here is one sample for a complete week. And then through this analysis of different types of molecular traces, we could identify the sources to these particles. And here we focus on the elemental carbon. So this is the soot. This is the black part of the particles. So it's called EC. And then we also focus on the organic carbon in the particles. So we haven't analyzed the inorganic components, which also contribute. So, for example, if we look at this sample here, then this is the contribution of elemental carbon from biomass burning, and this is the contribution of biomass burning or biomass combustion to the organic component. And then the gray ones here are the similar components from combustion of fossil fuels. What was really interesting in this study was that during the first part of the period, we had wind blowing from Central Europe towards Rotterdam when these samples were collected. And then during the last 2 weeks, the air came from the North Sea to Rotterdam. And you can really see a huge difference in the concentrations between these 2 weeks. We actually struggled a little bit because the levels of especially the soot were so high on the first samples. So it was difficult to analyze because it messed up with our techniques. So the conclusion was really here that the biomass combustion was a major contributor to these aerosols in Northern Europe during winter. And this is especially combustion taking place in the eastern part of Europe that's transported. And it's not the only study to show this. So I think it's time to have some good news. As I say, sometimes when you work with pollution, it's a little bit, it's so sad. And the good news is that the air in Denmark is actually getting cleaner. And it's not just Denmark, it's most parts of Europe. So if you look at this chart here, going back to 1983, and then we have the concentration of particles in microgram per cubic meter. And these are not the fine particles, it's coarse particles and somewhat larger. So you see back here, when I went to high school, the number was 100. And then around here, around 2000, so around the time when my children were born, the number was around 50. So in that time, we reduced the pollution with particles to 50% of what we used to have. And this is really thanks to large investments in cleaning of flue gas, so from power plants and so on. But also if you think about vehicles, cars, we have restrictions on emissions from cars. And this is really the product of all these different investments in science and technology. But as I said earlier, there's still problems in many places, and it's visible on this map made from satellite data. So these are fine particles again, and you can see really over here in China, in northern India, but also other places in Asia, there are large contributions. So these particles here, we know they're from different pollution sources, but you can also notice that sand and Sahara also contributes, so dust is also a contribution to particles. While up here we have Denmark, it's a little bit green, so not very high concentrations. So I would just like to thank my research group who has contributed to the research that we're doing, all of the collaborators that we have, the funding agencies of our research, and thank you for your attention.